Okay, so I will keep pushing this formulation of two-level quantum mechanics. Rather, I'll be pushing for the math of the two-level quantum mechanics, which my previous lecture I said could be formulated in terms of these coupled differential equations. And here we have a bunch of coefficients h00, h01, and due to the hermiticity of this Hamiltonian matrix, this is not some new number, but rather the complex conjugate of this off diagonal element. Okay, so yeah, so that's the kind of equation that one must solve. And the meaning of these coefficients was such that they are the coefficients that enter in the superposition of the basis states, which in this case is a zero state and a one state. And how these mixing coefficients change over time is basically what tells us how this particular two-level quantum system will evolve over time. Now, I said that this Hamiltonian matrix has to be Hermitian, but I did not say why it had to be Hermitian. So what I'm going to do today is to explain to you the reason behind the requirement for the Hermitian nature of these Hamiltonian matrix. Okay, so here's the thing. So let's do this normalization calculation. So if I take the inner product of a state with itself, then according to the usual analogy to the process of taking the inner product of a vector with itself, it gives you something that we call the norm or norm squared of this particular state. Okay, so here the viewpoint is that this state itself is kind of like a vector, and often this is called the state vector, because although what it represents physically is a quantum state, its mathematical properties resemble very, very closely those of a conventional vector that we learned about in classical mechanics. Okay, so the norm of these wave function is, you can calculate this right away from this definition, is alpha t norm squared plus beta t norm squared. Okay, and we're going to insist that although these complex coefficients may very well change over time, this normalization can never change. Never, 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 never changes. Okay, and the reason why I insist that this normalization be constant and not changing with time is because we want to make a probability interpretation of these numbers. Okay, so we claim that this is a probability with which the state can be found in the zero state. And similarly, this number here is the probability to find the state in the one state. And since the sum of all possible probabilities, the sum of probabilities for all possible events has to be 1. Otherwise, it's not even a probability. So that's where this insistence on the sum of these numbers being equal to 1 comes from. Okay, so what exactly do we mean by the probability to find something in some basis state? Well, okay, so here is where the idea of a measurement has to come into play. Okay, so this is some schematic drawing of a two-level quantum world, which is being described by this wave function psi, and then you apply to it some sort of measurement. Okay, I I draw these measurement apparatus in this blunt form because it doesn't really matter what kind of measurement apparatus I'm using. All I care about is the fact that this particular device has the ability to give out some signal if the state happens to be in the zero state, and there's a second device has the ability to give a signal only if the state happens to be in the state 1. Okay, so for example, you can think of the zero state as the spin up and the 1 state as the spin down, and maybe this apparatus is some sort of a magnet, and this magnet happens to deflect the spin up particle to the left and the spin down particle to the right, or something like that. Okay, so that can be a measurement apparatus. And when you bring such an apparatus to a quantum state, the only information you can get about that quantum state is in terms of either this apparatus making a click, indicating that they have just succeeded in measuring the zero state, or instead the apparatus gives out the signal which corresponds to the quantum state being in the 1 state. Okay, and I think I mentioned this a couple of lectures ago, that the way that these measurements actually proceed or happen is that although you may be trying to very hard to repeat the experiment in exactly the same manner, but still you're going to get different answers every time you do a measurement. Sometimes your apparatus will click the sign that a spin up state has been measured. Sometimes your apparatus will click in a way that's consistent with the spin down state. And then you keep repeating that experiment hundreds or thousands of times and make a histogram of the data, of your measurement data. Maybe then the histogram will look like this many clicks for spin up and this many stay for spin down. And you divide this number of events by the total number of events, which will translate into the probability of this of finding the state in the upspin state and the probability of finding the state in the downspin state. And now here comes the key interpretation ansatz of quantum mechanics. The interpretation ansatz of quantum mechanics is that this probability, which is something you can actually get to measure by doing experiment on a quantum system, is nothing but this number, which is the square modulus of these mixing coefficients. And likewise, the probability of measuring spin down is nothing but the square modulus of the second mixing coefficient in front of the second basis state. Okay, so now what I cannot emphasize enough to you is the fact that this sort of interpretation is not contained, is not contained at all within the formulation of the Schrödinger equation itself. All that Schrödinger equation tells you is just this, and how by solving this equation you can predict in a very, very precise manner how these coefficients will evolve over time. Okay, so if you just look at the Schrödinger equation, then just the Schrödinger equation itself, there's nothing probabilistic about the Schrödinger equation, right? It's completely deterministic. After all you do is just solve some couple differential equation, right? So there's nothing uncertain about it. It's just a piece of mathematical problem. You just go ahead and do your best to solve it. Now, when we say that quantum mechanics is inherently probabilistic, the statement comes from not the observation of the nature of the Schrödinger equation, but the second stage of interpreting these coefficients as probabilities for measurement. Okay. And this is some sort of an interpretation tool that people had to come up with in order for them to make a connection between theory, which is based on solving the Schrödinger problem, and the actual measurement or the actual experiment. When people go in and, let's say, measure properties of atomic vapor and so on, they're really measuring these quantities, and the way to connect what they measure with the predictions of quantum mechanics is by invoking this probability interpretation of these coefficients. So it is in that regard that we have to view the quantum mechanics as inherently a probabilistic theory. Okay, but I must emphasize again that the Schrödinger equation itself is not probabilistic at all. It's the interpretation of the solution of the Schrödinger equation which is highly probabilistic, and so what I'm stating now is something known as the Copenhagen interpretation. Well, there are many names involved, like Max Born and Niels Bohr and maybe Heisenberg. These early pioneers of the quantum mechanics, they came up with this interpretation of quantum mechanics, and so far, no one has really been able to challenge the interpretation as anything but true. Okay, but once we accept the idea of treating these coefficients as probabilities, then we must also accept the idea that this sum of probabilities can never be anything but 1. Okay, otherwise the probability interpretation simply breaks down at its foundation. So we have to stick to this. Okay, so now let's get back to the Schrödinger equation. The Schrödinger equation says that the coefficients obey this sort of dynamics. Okay, so then that means I can also compute these numbers like this. What's the rate of change of the alpha modulus squared? So it's alpha conjugate times alpha, so it's alpha conjugate d alpha dt plus d alpha conjugate dt times alpha. And for d alpha dt, we just read off these results. So h00 alpha plus h01 beta. And for the complex conjugate, we will find h00 star alpha star plus h01 star beta star. Okay, so I'm writing this as a h00 star because I have not yet implemented this assumption of a hermiticity. So at the moment, I'm just treating all of these coefficients, h00, etc., as some arbitrary complex numbers. Okay, now after making such a substitution, and then making some rearrangement, here's what I find. Okay, and you are really encouraged to derive these results for yourself. Okay, so if I multiply I on the left hand side, I get h00 minus h00 star alpha square plus, similarly for the h11, h10 minus h10 star. Okay, and in order for the probability interpretation to hold its place, we have to take this thing to be 0. Okay, which then would give us a constant value for the alpha mod square plus beta mod square, which we can then take to be equal to 1. Now, for that to be the case, of course, the most natural way to ensure that happens is by taking all of these things to be 0. Okay. But all of these things put together leads you to the nothing but the hermiticity condition. So if I take the Hermitian conjugate of the Hamiltonian matrix, then I will get back to itself. Okay, so the requirement of the Hermitian or hermiticity is required to preserve probability. And for probability interpretation of quantum mechanics. So the need to use only the Hermitian matrix in the Schrödinger equation is not simply due to any consideration of beauty or aesthetics or simplicity. It's really closely tied to the need to have a consistent probabilistic interpretation of the quantum mechanics. Okay, but then what about the three-level system? Maybe an n-level system. Okay, so for much more general n-level system, right? Because this probability interpretation obviously cannot be only valid for a two-level system, right? It must be valid for any level system of quantum mechanics. For an n-level system, then the wave function is a superposition of n different bases. Let me call this. Let me call it this way. And each one of these coefficients will satisfy the Schrodinger equation. Hij alpha j, and there's a summation over j from 1 to n. And from this Schrodinger equation, you can also derive what this square modulus would be, and therefore, and then you can sum this over all the possible bases, and the final result would better be 0. Okay, so then in order to meet this requirement, you will encounter a situation similar to what I have described here, and therefore presumably end up with the same condition as before, namely that these elements of the n by n Hamiltonian matrix be a Hermitian matrix, so therefore satisfy this relation. Okay, so this is what defines the Hermitian matrix to be Hermitian in terms of its matrix element. And I want to propose this as a homework exercise, since we haven't had any homework problem so far. So here's homework number 1 for this lecture. Okay, so obviously you can see I'm building a trap door into my lecture by putting down my homework problems at unexpected locations during my lecture video, so that without having to go through the entire lecture on video, you won't be able to realize exactly what the homework problem is. Okay, so I'm doing this so that you are certain to follow all my videos without skipping. All right, so prove the Hermitian nature of a n by n Hamiltonian matrix. Okay, following the mathematical considerations that I have just outlined for you. Okay, so here's the way you submit your homework. How to submit. Write down your answers, obviously. On a paper. Or if you have an iPad or similar device like me, or then you can write down your answers on tablet. And the tablet will automatically generate a PDF file for you. And if your writing is done on a piece of paper, then take a cam scanner. Do not take a photograph. Or if you want to take a photograph, make sure that you run it through a filter so that the background becomes white again. Otherwise, I won't be able to recognize your handwriting at all. So basically, run a filter in order to remove all the unnecessary background and smudges and all that. And so therefore produce a clean PDF file. And the reason why I request you to produce PDF is because if you upload your answers over 5 JPEGs, then I'm gonna have to open all 5 files, and that's really cumbersome for me. So there's a way to combine those 5 JPEG files into a single PDF. So please do that. Just do not upload those raw 5 different JPEG files. In fact, I won't be reading those kinds of upload. I only read the single PDF file upload. So make sure you follow this particular instruction. And then there's an upload page on I don't know exactly what was the title of that link, but there's a link on your iCampus website for this course where you can individually upload your homework solutions. Then I can access them from my side of the platform. And after taking a look at your PDF, I can grade. I can give out grades at the bottom of your upload. Okay, and then those grades will automatically accumulate, and toward the end of the semester, the total sum of those grades will contribute to the homework portion of your final grade, along with the midterm and final exam grades. Okay. The grading policy, or rather the final grade policy of this course, is I will give a maximum grading scale, which is like 40% A and the other 40% B or something like that. Okay, I will simply max out those allowed allocations. So if you are within this top 40% peer, then your grade will be either A plus or A. And if you're within the total top 80%, then your grade will be either B plus or B. Okay, so that's my policy, and I hope you like it.